All right, well, let's go ahead and get started here. So this is, let's see here. All right, 1 second here. Set up. All right, we're back. Let's go ahead and get started. So I'm Robert Heath. This is lecture number 7 of the Wireless Communications Lab. So what we're going to do today is we're going to finish up the discussion on constellations, in particular talking about how to make a constellation zero mean, how to calculate its energy, make it unit energy. We'll talk about computing the bandwidth, energy, and power of a digital communication signal. This is mostly a definition, but this is going to be important so that we can compute the performance of the system later. And then we'll talk about midterm number 1. And then proceed into the additive white Gaussian noise communication channel. This is the main communication channel that we're going to consider at least for the next few lectures. And this is how we're going to derive the detector and do performance analysis. This is a very common channel in wireless communication systems. Then we're going to review the receiver structure. And then if time permits, we will go through the optimum pulse shape design. Most of these sections are actually quite short, so ideally we'll actually finish all of them today. Okay, so with that, now let's go ahead and start with actually just a very quick review of linear complex pulse amplitude modulation. In particular, what I want to do here is I want to review the transmitter structure that we're considering in the class. In particular, that transmitter structure looks something like as follows here. There's some source of bits that is getting converted to symbols through the symbol mapping operation. And the input to that symbol map is this constellation set C. And that's what we're going to talk about a little bit later, and we also talked about that last Wednesday here. So the output of this is a sequence of potentially complex numbers S of n. That's our symbols. And then we get into these next two blocks that we will possibly talk about today or on Wednesday, which is create pulse train, and then perform. So the output of this create pulse train, this is like a block that's serving as a mathematical placeholder. We're going to replace it with something that's a little more practical in a couple lectures. But the output of the create pulse train block is something that looks like this here. So you might remember seeing something like this when you talk about sampling in a DSP class. There's like a comb filter. So this looks sort of similar to that. These are Dirac deltas, and the symbols are riding on top of Dirac deltas that are spaced by t symbol periods in continuous time. This quantity here is filtered by a transmit pulse shaping filter GTX of t, and then scaled by square root of EX to produce our baseband signal X of t. And remember that our baseband signal X of t, so if we convolve this pulse train with this GTX, we're going to put the G here and then scale the whole thing. So the transmit pulse shape, the transmit complex baseband signal looks like this: sum over n, S of n, GTX of t minus nt. And then we call this complex pulse amplitude modulation because these are complex. This is a pulse, and then this is a type of digital modulation. So that's what we're considering, for the next few lectures. And then towards the end of this lecture, we're going to talk about how this signal is impaired potentially by additive white Gaussian noise, and then how do we detect the symbols from that. And then later in a couple lectures, we'll talk about how to replace this weird operation here with something that you could implement in a DSP, and that's what you'll actually implement in the lab. So we'll replace this in a little while based on some ideas from multi-rate signal processing. So that's where we're going right now. So we're going to talk about the constellation, and then we're going to start talking about the structure of this pulse shape here. So now let's review the what we did last time. Let's see. Okay, so we're going to continue this discussion here of constellations. And in particular, we're focusing on this operation, which is the symbol mapping here, to produce these symbols S of n. And we have this ordered set C here, which has entries, let's say S0. Sometimes I'm using C. It doesn't really matter here. S0 through S of n minus 1 here. And this C, calligraphic C, is the constellation here. And these S's are the complex symbols. And then last time in class, we talked about how this bit to symbol map is essentially like a lookup table that maps sequences of bits, for example, something like this, to constellation points, and then how we could illustrate that. This, I'm just making up a fake-looking constellation here. And we could label these. And so the bit labeling just tells us how the bits produce this S of n here. So that's the symbol mapping idea. And then we looked specifically at this table here of common mappings. And several of these are used in wireless communication systems, in particular BPSK, QPSK, 4QAM, 16QAM, 8PSK, and 64QAM here. And in the lab, we'll implement primarily the BPSK and the QAM family. So we won't implement 8PSK, but I don't think we do QPSK, so we do 4QAM. Actually, this should be 4PSK. 4QAM is actually the same as QPSK, quadrature phase shift keying here. So these are some constellation diagrams here. And sometimes the labeling can be different. So in a standard, they will actually tell you which the preferred labeling is. So all the labelings here for BPSK, QAM, 16 QAM, 64 QAM have come out of the 802.11 standard. And then the 8PSK one I got out of the Edge GSM standard. Any questions about just this kind of bit labeling or these constellations here?
I saw for PSK it's the same as QPSK.
No, because the QPSK is the quadrature in QPSK means it's been shifted by pi over 4. So yeah, that's a mistake. I might have it in the book also. It's a mistake in there. But yeah, the 4PSK always has a point here. And so all the PSK family always has a point there at 1. And then you just keep adding density. Like we could have NPSK, we could put M points equally spaced on the unit circle here. So any other questions, comments? Now one thing that you should realize from looking at these plots here is that there's a lot of structure in there. You know, these are not arbitrary points like I just drew in this previous example here. I just sort of scattered 4 points there. These constellations are very, carefully constructed here, and the points are spaced reasonably far apart. And so we're going to see when we do performance analysis that there's a quantity called the minimum distance, which is the minimum distance between any two constellation points, looking at all the points. And having that minimum distance be large is a good thing. And so generally constellations will try to be as spread out as possible. And so there's a reason for that. And there's a reason they're not spread too far, and that's the energy normalization, and that we'll talk about today. So there's features here that we're going to get to later in class, either today or in subsequent lectures. All right, so now let's just talk a little bit about some of the things that you need to be able to do with a constellation. These are mathematical manipulations that, to some extent, are operations that you would do on a homework assignment or an exam, but you do occasionally, for implementation, also need to do these normalizations. So I'll explain that here. So let's talk about constellation normalization here. Okay. So the assumptions that we make about constellations, there's 3. And these are not always made, so you have to be careful if you're using another reference that they follow the same set of assumptions. They don't always do that here. So the first one that we assume is that the symbols are equally likely. So what this means is that if we have a probability mass function Ps of m associated with the mth constellation point, so this is the probability that we select S sub m in this constellation here. We're assuming they're equally likely, and there's m points in the constellation. That means that probability is 1 over m here. So we need this for some calculations. For the most part, wireless systems are designed to ensure that this assumption is reasonably good. And even if it's not a good assumption, there's going to be scrambling and other features to make this approximately true. There's now it turns out that from an information theoretic perspective, this isn't actually the best thing you can do. There's a way to make them non-equally likely that can even be better, and that concept is used in these old voice band modems, but we actually don't need those. We don't need that in most wireless systems here. And the performance difference in theory between non-equally likely and equally likely is pretty small relative, and also it's hard to implement the DSP if they're not equally likely. It introduces a whole bunch of complications. So we're always going to assume this, and most books will also assume that without even telling you, so that's not a big deal. Now the second one is that we're going to assume the constellation is zero mean. And so what this is going to mean is that the expectation of this symbol sequence S of n, treating it as a discrete time random process, is going to be 0. And this is usually the case in most books as well, also without telling you. And it's true for almost all constellations. I can think of one special case that's not. And then the final thing is that we're going to assume that it's unit energy. And this is particular to my approach in the course. This isn't always the case here. And what it means as unit energy is that the expectation of the magnitude squared of that constellation sequence, assuming it's zero mean, so we're not subtracting the mean, is 1. And so what you need to be able to do is if I give you an arbitrary looking constellation, you need to be able to determine if it is zero mean and otherwise correct it. And if it's not unit energy, determine its energy and otherwise correct it. And so that's what we're going to do now. So we'll talk about zero mean and constellations, and then the unit energy property here. Okay, so first of all, if you're given an arbitrary constellation, so let's use for this sake of the next few pages here, this, constellation with points s of 0 to s of n minus 1 here. So if you have to compute the mean, let's call that mu of s. That's the expectation of s of n. That's going to be 1 over m, the sum from m equals 0 to capital M minus 1. This is a little m here. Hopefully it's not too confusing with this s of m. Now, we don't have the probability in here is 1 over m. So that's what this 1 over m is here, right? So we're computing the expectation of just a finite valued sequence here. It's a finite valued random variable. And because they're equally likely, this right here is the ps of m mass function here. Okay, so I mean, that's the mean. That should be easy to compute, given what you learned from previous courses. Now, then, the question is, if this is not 0, what do you do? Well, just like what you would do in, you see this in probability when you're trying to do computations with Gaussian random variables, for example. What we'll do is we're going to come up with an equivalent constellation that has 0 mean. And so what we're going to do is we're going to subtract off the mean. And so we form a new constellation. We might call it C bar here, where we take each symbol, we subtract the mean, and that's it. So we just distort the constellation as appropriate here. And so the operation intuitively here, like if we were plotting, I'll do an example later, but supposing that we had like a constellation that looked like this. This is the real part, this is the imaginary part here. Intuitively, what's happening is by having it 0 mean, we're making the center of the mass 0, and so we're going to come up with some new constellation that ends up being centered. So this point here would be us, and now the mean is 0. So intuitively, that's all we're doing here. So this is for the most part just something you need to be able to do on the homework. Any question about 0 mean, making it 0 mean? All right, so let's talk unit energy now. So unit energy, now this assumption is used for several reasons. So one, it's used in the performance analysis so that we can separate out the effects of the transmit power from other features in the DSP. And for us in particular, what this allows us to do is this allows us to put all the gain, or power, if you like, into this square root of the x term here. So what we're trying to do is, in our communication signal that we're writing like this, all the normalizations in this class are going to be done such that all the gain in the signal here is square root of the x. So what we don't want to happen is that you can have a constellation that's got points plus and minus 1 million, and somehow that makes the signal much bigger than it should be. We want to factor all of that out and incorporate everything only in the square root of the x. There are other reasons to do that too. One is that when we actually create this signal, we're going to find that all the gain is really added in the analog. It's not added in the digital. So we're going to have a digital to analog converter that outputs a maximum value of, say, plus minus 1 volt or plus minus 5 volts. And all the gain is going to be added in amplifiers in there. So there's no notion of digital gain. You could potentially attenuate the signal a little bit digitally, but because there's quantization and other issues, that's normally not something that we do. So in reality, all the gain is in the analog as well. And so by doing this, this allows us to create kind of a gainless digital signal. Now, one question you might have is, what about this GTX here? Well, we're going to get to that later. But we are also going to have a normalization assumption on this GTX too, to make sure that we don't add any extra power. So for the unit energy assumption, essentially what we need to do is, first of all, let's look at the definition here. So essentially, I call this E of S. So energy of a constellation is the expectation of S of n magnitude squared, everything magnitude squared because it's complex. And then because it's equally likely, we can rewrite that as 1 over m. That's the probability mass function. The sum from 0 to m minus 1, S of m, magnitude squared. So that's the energy here. And then we want to design the constellation such that this energy is equal to 1. So if you don't have a unit energy constellation, then you need to take one that you're given and modify it, essentially rescaling it here. So suppose that you have some constellation C is already 0 mean. And what we want to do is we want to find an alpha such that this modified constellation, let me call it C hat here. Actually, I think in the book I use C sub alpha, so I'll call it that here. Where I take each constellation symbol and I multiply it by alpha. And we want to make sure that this resulting constellation has unit energy. So we want to pick the alpha as appropriate here. And so you can go through here, so let's plug in this over here, right? So we plug in here, we're going to get 1 over m times the sum from m equals 0 to m minus 1, alpha S of m squared. But we have alpha common, so we can factor it out. So we get that alpha squared over m times the sum from m equals 0 to m minus 1, S of m squared is equal to 1. So therefore, and then alpha scaling factor, so because we have the magnitude squared here, we can just arbitrarily assume it's real. And we're going to assume it's real and positive. I suppose you could have a negative, but it doesn't make any sense here. So we're going to have this be square root of 1 over m, sum from m equals 0 to m minus 1, sum over Sm squared here. So that just gives you the distortion factor that you need to create a constellation that is equivalently unit energy. And then the intuition of this is that we're going to take our constellation, just as that example I had before, that has points, whatever here, we're going to scale it so that the new values are, so supposing that this was, for the sake of argument, let's say it's 100 and 100. We're going to scale it to some new values, alpha 100, such that the energy of that thing is 1 there. So I guess I should have shown this potentially squishing down quite a bit. So we're not going to rotate it and flip it around. We're just going to push it down. And then, any questions about the energy here? I'll do one very simple example, but any questions? No. Okay, so just the example being, let's suppose that we have to think of this to make the numbers work out well. Put 2 and 6, yes. All right, suppose we have a constellation here of 2 and 6. We want to find a zero mean equivalent here. We compute the mean, 1/2 of 2 plus 6, 8. It's going to be equal to 4. So we find this equivalent constellation, 2 minus 4, 6 minus 4, which is minus 2 comma 2. So you could plot this constellation here. We had 2 and 6. This one here. Now we've got minus 2 and 2. And then we compute this alpha here. So it's going to be 1 over square root of 1 over 1/2. 2 squared plus 2 squared. So it's 4, 8. Let's see. 4 is 8. Divided by 2 is 4. 1/4 equals 1/2. So then the normalized constellation is 1/2 times minus 2, comma 1/2 times 2, which is just minus 1, comma 1. And we end up with this BPSK constellation. So anyways, that's just something you'll have to do in the homework. Okay. All right. Any questions on that?
The first two assumptions have been taken just to make the thing simpler to compute, or is there any other reason also?
The normalization assumptions, the three?
The normalization you explained, but the first two, that is zero mean and likely thing.
Zero mean and what was the other one?
Equally likely.
Oh, equally likely, yeah. So the equally likely, yeah, okay, right. So okay, so the zero mean assumption, I should have mentioned that, is also there because DC doesn't propagate. So if we had a non-zero mean signal, that would mean that our x of t was also non-zero mean. But you can't send a modulated signal that has a mean, and so that has essentially a DC value. So this is just a way of ensuring there's no DC. And there's like different transceiver structures that give you DC offset that has all these problems with DC components. So it's actually there to make sure the analog signal has some properties. And so most communication signals, I mean, it's a zero mean, or they might even explicitly make the DC component disappear. And we'll see how they do that in OFDM signals. The equally likely assumption is going to be there for the purposes of our performance analysis. So it does simplify things, but it simplifies things in a way that reflects the assumptions that are how we usually design the system. So the system is designed to make sure those bits look roughly equally likely.
Yeah, but the way we corrected here, we won't be able to correct. I mean, will we be able to correct the equally likely thing? I mean, it's not equally likely.
No. No, we haven't talked about that. And further, we wouldn't want to correct it, actually. If it wasn't equally likely for some reason, there's essentially what it means is that the bit sequence is not equally likely. And so that means that there's some sort of structure in the bits that, for example, should have been fixed by your compression algorithm. So if you had a source that is not generating IAD bit sequence, that means there's a lot of redundancy left in it. And then that would be a problem. Or in this case, it would mean that the channel code has structured such that the bits don't look equally likely. And that...
How will we counter that?
We don't really counter it. I mean, we're not going to deal with it at all because it's just not an issue. Because like I said, the system will use scrambling at a minimum to make the bit sequence look as random as possible. So with a scrambler, you essentially take a sequence of bits and you multiply it in the binary field by a pseudo-random sequence that's very long, say 100,000 bits long. And so then that even if you have a string of all zeros, that'll make it look random looking and ensure effectively zero mean. So we don't need to correct for it. We don't really need to account for it. You won't even see this normally in an advanced course either. You won't see it. It's just not needed. The only place it comes up, to my knowledge, is in these voice band modems. And there they have a very special coding structure to create a set of constellation symbols that are not equally likely. And it's really cool, but it requires a very complicated decoder. And they do that because they have to get so close to capacity, they need that extra little bit of complexity. And we just don't need it in wireless. I suppose we could use it, but it's unused. Any other questions? Yes?
Can you tell us a little more about PSK and temperature and how do you come up with the constellation?
Yeah, I think that's a good question. Go back over here. So the PSK formula is the constellation symbols look like e to the j 2 pi little m over capital M. So that's actually the formula for that. That's fine. The QAM is the concatenation of PAM in the real and imaginary. And the simplest, I'm trying to think of the formula here. Let's see, it's going to be 2. The difficulty here is the normalization, because normally when we talk about QAM, if I was to zoom in, you possibly can see it here. There's like a square root of 7/6 here. I got this from applying the normalization, but normally if you like open up a book, you would see the 64 QAM would be spaced on, this would be like 1, 3, 5, 7. This would be -1, -3. This would be 1, 3, -1, -3. So this is normally how the points would be specified. So it's going to be like plus minus 1, 1 plus j, 1 plus 3j, 3 plus 1j, and so on. And then you apply a normalization to get this, what I have here. And to do that, you have to follow the procedure. And so in 802.11, for example, they'll actually specify for us the scaling factor. And they use a slightly different scaling factor here because having something like a square root of 7/6 would be inconvenient to compute. So they tweak it a little bit. So it's not quite unit energy. Okay. Any other questions? Yeah.
For the value of alpha, should there be another nesting of indices for the denominator?
Possibly. Let's see. This here?
The last page.
This here, yes. Yes. All right, so any other questions? Okay, all right, so that's constellations. Now, let's talk about the bandwidth, energy, and power. So this is essentially just going to be a definition. So it's going to be short. So this is bandwidth, energy, and power of x of t here. Now, the x of t formula, again, I'll write it out. Square root of Vx, sum over n, S of n, g tx of t minus nt. So this is the complex baseband signal that we're sending here. One of the complications here, so first of all, if S of n here is a random process, x of t is also a random process in continuous time, but it's actually not a Whiteson stationary random process, unfortunately. The technical term is it's a cyclostationary or random process. So x of t is so cyclostationary random processes There's a whole theory of these. There's a few books on this topic. Gardner's book is a classic example here. They're essentially random processes that have periodic structure in the correlation, but so it ends up with a two-dimensional correlation that has periodicity instead of a one-dimensional correlation. You probably don't see these in even in the more advanced probability course, but they are used in certain special cases. They're used in particular in communications for a problem that involves modulation identification, where suppose that you were a, let's say, government agency that was listening to spectrum and trying to determine if there was a digital cellular signal in that spectrum there. So if you know that wireless signals are generated according to this process here, then they'll have some sort of cyclostationary statistics that you could then use to estimate. And you could actually find things like estimate the symbol period, and you can estimate this other things here. So anyways, there's application of this. What it means is that we can't really compute the power spectrum in a straightforward way. So what I'm going to do is I'm going to give you the, using some results from cyclostationary random processes, we can essentially define, and this is defined in the same way that we define a Fourier transform for a periodic signal using its Fourier series coefficients. Kind of skipping some technical details here, but we define the power spectral density of x of t as px of f. And it's going to be ex over t, expectation of, so this is expectation here, of s of n times gtx of f squared. Now, because we've assumed that the constellation is unit energy, this is 1. So for our purposes in the class, this quantity here is going to be ex over t times gtx over f squared. Now, the way I've defined power spectral density, even though we're not going through the details, does respect this property here. If you plug in this x of t into a spectrum analyzer, you will get something that corresponds to this. So this is a reasonable approach. I'm just not going through all the technical details for it. What this says is two things. So first of all, you've got an ex over t here. Now, the units of this would be joules per second, which corresponds to what we think about as power. So for power spectrum, this actually makes a lot of sense to have a t here. And then this gtx of f here, what this means is that the spectrum of that pulse shape determines the spectrum of our signal. So what would happen if we used a square wave as a pulse shape? Anybody remember the Fourier transform of like a rectangle function? It's like a sink. Yeah. Not band limited by any stretch. So that would be bad. So we're actually going to use smooth pulse shapes. And so we're going to derive, if we have time later today, some formulas that start to tell us what good pulse shapes look like. But if we want to make this band limited, we can't use the simple ones that we always think about, like a square wave. It won't work. Won't make it band limited. So if we want to make the signal band limited, we have to play with the pulse shape here. So that's the first major point here. So let's see. So gtx of t determines the bandwidth of x of t. All right. Now, what about normalization here? What about power? Well, so we also have another normalization here. So we're always going to assume that the integral of gtx of f, which by Parsevals is the integral of gtx of t, is equal to 1. So we call this, essentially it's a unit norm pulse shaping assumption. And by doing this here, when I integrate out, this quantity here, if I've done this correctly here, then I get this EX over T here. When I'm done, which is the transmit power. And this is EX is, we also call this energy per symbol, and this is the symbol period. So this is symbol energy here. And so all I'm saying here is that we're going to normalize that pulse shape so that it also doesn't add any energy into the signal. And actually, this is also perfectly reasonable for the same reasons it makes sense to normalize the signal power, the constellation as well. So keep that in mind that we will need this, this constraint at some point. So any questions about this here? So essentially, bandwidth is determined by the pulse shape. We normalize the pulse shape so that we don't add any extra energy. And based on what we know about bandwidth, that doesn't change the bandwidth because the bandwidth, notions were all relative, right? So if we had like the 3 dB bandwidth, if we scale the whole signal by 100, by the pulse by 100, it doesn't matter because it's 3 dB bandwidth is still the same. So that doesn't change the bandwidth properties. It just makes the normalization suitable for the analysis and also for the digital implementation. All right, no questions? So if you had to normalize a pulse shape, compute its energy. If it's not 1, you divide by the square root of that. So pretty easy. All right, let's just changing the numbers here. Okay, so let's stop for a second here. Oh, shoot. Forgot to show my, this is my computing energy and bandwidth slide here. We'll have to cut that back in the video. That's annoying. All right. Intermission here. I am sorry to discuss something that is not as fun as normal, but I did think it was fair for me to remind you that midterm number 1 is coming up. It is October 2nd. The exam will last 75 minutes. It will be in this classroom. You will be allowed 1 page, 2 sides of handwritten notes. So let me clarify this a bit. This here is a piece of paper. You all see this here? It's a piece of paper. We're using the American size piece of paper, 8.5 by 11. Don't use A4, 3, 2, whatever. American piece of paper here. And this right here, you see this? What I'm doing? This is called handwriting. Yeah. Some of you here, maybe you've been in my previous class. I mean, really every semester someone photocopies something on their sheet and then gets really mad at me and gives me very low evaluation because I don't let them use the photocopied book, solutions, homework, or whatever. The whole point of giving you 1 page, 2 sides is so that if there's things that you feel like you don't want to memorize, for example, Fourier transform tables, that you have an opportunity to write them down. That's really all it's there for. It's not really there so that you can have the book in small form. I don't care that you know how to use a copier, you're a whiz at scanning. That's great, but just not the point here. So again, handwritten notes. Now ideally this is handwritten by you. I have no way to check that. I suppose someone in here could handwrite 27 cheat sheets and sell them to everybody. I'm not saying that's a good thing, but one could do that. I can't check it, but really you should be doing it yourself. Calculators are not allowed. What this means is that I will try to make the problem such that the numbers are not really terrible. That doesn't always work most of the time, because I usually solve it wrong the first time I do it. And then later on, I give you the exam, and I'm whacking myself like, man, that was much harder than I thought. Calculators will not be allowed. There will be 4 total problems, one of which is a lab problem. So I will post up some of the previous midterms so that you can see the lab problem. All of the problems I've given before are already in the course notes. So, I mean, you can see them in the notes. You'll see that they'll be like, midterm problem, blah, blah, blah. So just look in the chapters for other example midterm problems. So for the lab problem, typical lab problem will require you to do something with LabVIEW. Perhaps correct some LabVIEW code. It could be sketch out some LabVIEW for something. It could be talk about something that was from the lab. The point of the lab problem is to see that you're learning LabVIEW, that you're learning the material in the lab. Because it is a risk with having 2 lab partners that someone maybe, oh yeah, I'll do the LabVIEW and you do the lab reports, and yeah, that will not be a problem here. What's that?
We have to
Bring a computer.
because of that
No, there's no computer here.
LabVIEW problem.
Right. Right. Just like if you take like a programming course and you have to write down some code for something, it'd be in the same way here. I mean, yeah. So you can't search in the for the VIs and all of that. This is not going to be. It's not like that. It's not a comprehensive exam of your knowledge of LabVIEW. It's really more that you're doing. You're participating in the creation of the labs and that you understand what's going on, ideally. And these problems, are usually challenging to grade. I'll say that. Ideally, the problem isn't challenging, but they're always just a pain to grade. So we'll try to make it as easy as possible within reason. Okay, so that's the midterm here. Also, the plan is Yingjae will have extra office hours on Tuesday. I've asked him to schedule something like 8 office hours between Monday and Tuesday. I will be gone on Wednesday, so he's going to proctor the exam, or one of my colleagues will proctor it. But I will try to answer questions in email if you have them here. Okay, any questions about this midterm number 1? Yes.
But will we provide like any tables or such, or if there's like some Fourier transform, we have to handwrite those?
Yeah, that's a good question. Yeah, so I will not provide tables. So if you don't know the Fourier transforms, then yeah, you can write them down. But I mean, if I was to give you a strange Fourier transform, it would ideally, you could derive it from your knowledge of the tables. Now, I probably, I won't say for sure, but most likely I would not give you one that you had to calculate directly using the integral or the sum, just because that's material that's already been covered. What I'm more interested in is that you can use the properties and the tables to do Fourier transforms quickly without having to do the integral and everything. Because that distilling the knowledge of the table into your head is what's giving intuition. You see something happening, you're observing a signal, it's distorted, you don't know why. If you know those transform properties, you can often figure out what's wrong with the signal, right? You can't take that signal. I mean, I suppose you could plug it into MATLAB, compute its Fourier transform, but it won't give you any insight. So this is the reason for that. And yeah, ideally you should know the basic properties. Other questions? Midterm? Number 1. No? See a lot of smiling faces? Yeah. All right. Everyone's getting psyched for it. Midterm number 1 is coming. Yes. It's coming around the corner. So it'll be fun.
Which lecture are you stuck on?
What's that?
Which lecture are you stuck on this test on?
This is going to be everything that's included in the homework, so it's going to include some material from today. And I forget exactly where it cuts, but essentially, I think I had a constellation problem on the homework, so it's going to include up to constellations and pretty much whatever we covered today in the lecture, but probably not Wednesday. Actually, let me think here. So I may have some concept from may have some concept from Wednesday, but it'll primarily be everything that's been on the homework. All right, any other questions? All right. So now we go back to lecture at hand. So now we're going to talk about the additive white Gaussian noise channel. And so you should be able to define this channel and compute SNR. Okay, so this is also, kind of just a definition of sorts, and it's important though because this mathematical model is what we're going to use to derive the structure that should be in the pulse shape, and we're going to do the basic performance analysis. So the additive white Gaussian noise channel is a mathematical model for a particular type of distortion in communication signal, which is additive. So this is our complex baseband signal x of t. This v of t is noise, and the resulting signal is y of t equals x of t plus v of t here. So I'll write this out at least once here. Additive white Gaussian noise and this is a good model for thermal noise. And so this kind of impairment can be added anywhere. It's added to your signal at the transmitter. It's also added to your signal at the receiver. It turns out that at the transmitter, the signal level is very large, right? Because there you might be talking, volts, because you're sending signals with a milliwatt or a watt of power. It can be, the signal level there is pretty large relative to the noise power. But at the receiver, the signal level is so small that that little bit of noise impairment from electrons moving around creates something that causes a huge amount of errors in the communication system. And so primarily, when we're talking about Gaussian noise, we're talking about the noise that's added at the receiver. And normally this is the noise that is added in every component, but it's normally the noise that's right at the front end that's the most important. So essentially that's it here. So V of t, what this means at AWGN is that this is a IID complex Gaussian random process. And we've gone through this before here, but essentially V of t, in particular for thermal noise, we're going to write it like this. So it's complex Gaussian with zero mean, variance sigma squared. And for thermal noise, the sigma squared is equal to n naught, which is equal to k times TE. So this n naught is n naught, and this is Boltzmann's constant. And that's, let's see, 1.38 times 10 to the minus 23 joules per Kelvin. And this is the effective noise temperature of the device. So again, we're talking about here the receiver. So if you haven't been given any other information, you just assume that the effective noise temperature is more or less room temperature, 290 degrees. If you take one of our classes on RF circuits, you'll go through how to calculate the effective noise temperature of a cascade of different RF components. And that's a fun exercise, but we don't do it in the class here. So this is essentially it here. So the additive noise is complex Gaussian. It's zero mean. The variance is a function of the temperature. And the real and imaginary parts are independent and uncorrelated. That's the complex Gaussian assumption here. Now, because of the what's called this white assumption, the covariance function for this Gaussian noise sequence is just sigma squared times delta of tau. So it's a delta. So that means it's in the frequency domain, it's completely flat. So this is what the spectrum of this kind of noise looks like here. So it's very flat. So wherever your signal is, so if you have a signal right here, when you integrate over all of that to compute the noise power, you're going to end up with this n naught times the effective bandwidth of your signal. So as you increase the bandwidth of a signal, you're going to accumulate more noise. And then finally here, it turns out that the measure of performance that's important in a communication system with additive white Gaussian noise is called the signal-to-noise ratio, which we abbreviate as SNR. And the signal-to-noise ratio ends up being essentially expected value of the signal divided by the expected value of the noise power here. And we have to be a little bit careful about this here because of the notion of bandwidth, but basically what we'll see is that this ends up being typically EX over N naught. There's a factor of T in there. That factor of T cancels the fact that we're integrating over the bandwidth here, so it's something that we'll look at a little bit more carefully in possibly later today or in the next lecture. But so generally speaking, in the additive white Gaussian noise channel here, what determines how well you can communicate in the channel is the ratio between the signal power here and the noise power here. Now, if you study communication systems for a long time, it seems obvious. But I assure you there's nothing obvious about this because this comes from detection theory. And if you have a different kind of noise here, you don't get this at all. There's nothing sacred about it being the ratio. For a different distribution or a different kind of impairment, you can get something totally different here. It could be the sum. It could be anything else. So don't take that for granted everywhere. But primarily, we will see that the signal-to-noise ratio, at least for this class, is the most important quantity here. Okay. So any questions about this?
If SNR is less than 1, then can we detect the signal?
If SNR is less than 1, okay, then what's your question?
I mean, if signal is lesser than noise power, then can we detect the signal?
Yes, it turns out you can detect it. But you're actually not asking the right question, right? So the real question is, how well can you detect the signal? So it depends on various other sundry things. But, if the smaller the SNR, the more errors you will make. So we can never detect the signal perfectly, at least unless we have enough coding and interleaving over a long period of time.
Still, we can detect if it is less than 1.
Yes, you can communicate at less than 1. So we normally will talk about SNR and dB. So 1 will correspond to 0 dB. And yes, you can communicate at less than 0 dB.
Then in that case, we recover signal by some properties of the signal because noise level discrimination is gone, right?
Well, this is why we have to talk about what does it mean to detect. So we'll talk about that a little bit in, it's got to be Wednesday, I guess. So we derive what does it mean to be the optimum detector. So really, again, the question is performance. If you make 1 symbol error out of every 5 symbols, is that good enough or not? Or 1 out of every 100 symbols? What is the target error rate that your system can support? Because you're going to have coding on top of that. So it's really the coding that lets us fix all of these errors. And even with coding, though, you're still going to make errors. So the whole system is designed not to be error-free, but it's designed to work with errors. So the raw error rates may be, we make 1 in 10 bit errors. And then with coding, that becomes 1 in 1,000. And then we use a retransmission protocol on top of that to correct for frame errors. And then there's, so every layer of the kind of the network is designed to deal with these errors that can happen. So, but it doesn't work well below 1.
Because there is a term like radar cross section or sigma naught. So we define it based on the SNR equal to 1. So that's why I had a doubt whether lesser than that it can detect or not. Because we generally say that it's the performance of the system.
Yeah, and the reason is that, so a lot of this detection theory comes from radar. The difference is that there, you typically want to detect with a much higher probability, right? So like if you miss an object 1 out of every 3 times or 1 out of every 5 times, that's pretty bad. But here, it can be okay because we have coding on top of this. And that coding is very powerful. And you don't have that concept, as much in radar because you're sort of, shooting a signal and looking at the observation. So here, the intuition for me is that, we're not sending one symbol. We're sending a whole long sequence. And that whole long sequence has structure. And so by sending that long sequence, if we have an error in the beginning of the sequence, we can use information at the end of the sequence to help fix that at the beginning of the sequence. And there's a lot of redundancy in that sequence from this error control coding. Okay, any other questions about this? So in short, this AWGN, this is our biggest enemy in communications. Now, another one is going to show up too. That one's called fading. That one shows up later in the course, but and that's particular to wireless. But communication systems, noise is our biggest enemy here. Now, it's not all thermal, by the way. If you're building a communication system that communicates with satellites or a space-based system, you also pick up galactic noise, and you can pick up noise in different ionospheric bands depending on where you're communicating. So thermal noise is one of a possible suite of noises, but it's typically the only one that's included in terrestrial mobile cellular. We don't look at these other kinds of noise because our antennas aren't looking up at the sky, and they're looking around and they're receiving relatively large valued signals.
Isn't multiplicative noise predominant in these systems?
Yeah, so there's a notion of multiplicative noise that can happen, and there's several ways for that to come about. It's also important. We don't talk too much about it. So one would be phase noise. You can model as multiplicative noise. Another, you can model fading as multiplicative noise, and that we will consider. But in itself, multiplicative noise is an important effect, but it's probably like the effect to consider after considering thermal noise. Okay, wait a second here. All right, so the time we have left here, I think this is probably all we'll get to here. We're going to look at the transmitter and receiver structure that corresponds to the kind of signals that we're postulating here. And so what you want to be able to do here is draw this block diagram out and explain the different functions. So we're going to just review this AWGN transmitter and receiver. So what's going to happen is, as we go through the course, we're going to add other impairments besides noise. And we're going to make the receiver in particular more complicated. So this is like the first of several steps that we're going to take. So the transmitter structure that we're assuming is the same one that we've had before. And this structure won't change too much. Actually, it gets modified a little bit, but it doesn't change as much as the receiver. So again, we have this symbol mapping. We have this weird pulse train block. We have the pulse shaping filter. The scaling factor, and then the X of t here. So that's the transmit structure, which we've seen before. So let's talk about what the receiver structure is going to look like. Now, it turns out that the receiver structure has the following form here. So we're not going to like derive the form from first principles, but we are going to derive the components of the form. So first of all, we're going to take our y of t. That's our signal that's been distorted by noise. We're going to take that y of t, and we are going to filter it by a filter that's called grx of t. After that, we are going to sample. And this is important here. We're sampling at the symbol rate. Not sampling at the Nyquist rate. And we'll see that they're not necessarily the same thing. So we filter the signal, we sample it, and then, now here is where this block that's called detection fits in. So we might call this, I sort of use different terminology here, but let's call this W of n, Y of n here. Sometimes I call this Z and then this Y. So supposing that this is our sampled sequence here, this goes into a detection block that produces at the output an intelligent guess of the symbol sequence that was sent, S hat of n. So that's why I'm putting the hat here. Hat is always like estimated or detected quantity. Not always, but it's just convention. And then it passes into the inverse symbol mapping block. That's this block right here. And that produces our estimate of the bits that was sent here. So of the functions that are up here, the symbol map we've talked about, the pulse train, the transmit filter. Now for the transmit filter, all we've done so far is we've said that it determines the bandwidth of our signal and it's normalized. Otherwise is yet to be unspecified. So we need to determine a good transmit pulse shaping filter. At the receiver here, we have this filter here. Let's call this the receive filter, grx of t. That also is unspecified. Now you might wonder why we need a filter here at all. Well, the answer really comes back to, remember that noise spectrum. That noise spectrum is flat. So if we don't filter it at all, we're going to pick up noise from here to terahertz, which is not good. So at a minimum, we want to filter just to band limit the signal so we don't pick up extra noise. But we're going to show that that filter actually has a very special property that's going to be called a match filter. So it's going to turn out that this filter is going to be related to the choice of the pulse shape in a very particular way. So that's what we're going to see based on the 4 minutes we have left. We're going to see that on Wednesday. And then the final piece here is the detection block here. So the role of the detection block is we're going to take, as an input here, we're going to take this constellation C, and we know the possible points in C. So Y of n is going to give us essentially a noisy constellation symbol. So we have to figure out which one was most likely to have been sent according to some probabilistic rule. And so then that will lead us to the maximum likelihood detector, which will be an algorithm, not exactly a mathematical, we'll express that as a mathematical optimization, but it will be something that you essentially can solve with a little algorithm. And that will be the detector here. And so that detector will take this Y of n, which is just some complex number, and it will output one of a finite set of symbols according to this detection rule. And naturally, you want the detection rule to be one that gives you very few errors, because digital communication system, bad things happen, we have a lot of errors. So we want to have as few errors as possible. So we have to quantify what that means, and we're going to use the likelihood function to define our detector. And so we'll go through on Wednesday. We will define the it's either Wednesday or the following Monday. Definitely Wednesday. We will derive the transmit and receive pulse shaping filters that maximize the received SNR. So that's what we're going to do. And then, I'm trying to think here, we either talk about how to implement these pulse shaping filters. Yeah, I think that's what happens next here. So where we're going here is we're going to derive the GTX and GRX of t to maximize the quantity which is called the S signal divided by interference plus noise, or SINR. This will be something that's called intersymbol interference. This will be noise power. This will be signal power here. So what we do Wednesday is we find partially a formula here for GTX and GRX to maximize this quantity here. And we're going to take into account the fact that the pulse shape has to be unit norm, and we're going to find that it has to satisfy a very special property. It's called the Nyquist pulse shape. Then we're going to talk about families of functions that satisfy that property, and then how to implement them here. So, and by how to implement, what I mean is that we're going to look at how can we get rid of this block here and replace this with something that involves a discrete to continuous converter or a digital to analog converter, because this right here doesn't correspond to anything we can build in the circuit. So we're going to essentially show how we can do this with digital filtering and discrete to continuous converter. And then similarly, at the receiver, we're going to replace this set of functions here with a continuous to discrete converter operating at the Nyquist rate, followed by digital filtering, followed by subsampling. So we're going to use some tricks from multi-rate signal processing to essentially enable us to convert these into pieces and digital functions. So that's what we're going to do Wednesday. And then the following week, we will derive the ingredients of the optimum detector here. So that is it. Okay, so just to summarize here, that's what we've done today. This was lecture number 7. We reviewed this linear complex pulse amplitude block diagram. Reviewed the concept of constellation. You should be able to draw the constellation diagram, including the bit labels. Calculate the energy of a constellation and normalize it. You should be able to compute the bandwidth, energy, and power of such a complex pulse amplitude modulated signal. Find the additive white Gaussian noise channel. And then produce and explain the key components of the additive white Gaussian noise transmitter and receiver. And we will optimize these components during subsequent lectures. So that's it.